Okay, good morning, everyone, and welcome to the workshop on programming language standardization and specification. We are so glad to see all of you here today. My name is Mikhail Barash. I'm an associate professor at the University of Bergen in Norway, and I'm co-chairing this workshop together with Yulia.
Good morning. My name is Yulia Startsev. I'm a senior staff software engineer at Mozilla. I work on the SpiderMonkey compiler, and I'm co-leading the language design topics within our team. I'm actually currently on leave until July 2026, so if you want to get in touch with me, I might be very slow. But this workshop has been in planning for the better part of this year, and I'm quite excited to be here. The subject we're discussing today, that of programming language design and how it intersects with specification, is one I find really fascinating. Specification can have a very large impact on the design decisions we can make or that we want to make. And I hope we have the opportunity to have deep and insightful discussions today. This workshop comes out of the research task group TG5 at TC39. If you're unfamiliar, TC39 is one of the technical committees of ECMA, and it is the technical committee responsible for the design and specification of ECMAScript, which is better known as JavaScript. While the work of TG5 is highly focused on one specific language in its design, we're always looking to learn from other languages. And the purpose of this workshop is to bring together a broad range of language design communities and discuss, both in terms of scale and scope, what similar challenges and different challenges we might be facing.
Right, so whether you are building tools, writing specifications, or just trying to keep your implementation in sync with the ever-evolving semantics, our goal today is to discuss where those challenges meet solutions and where creative, rigorous thinking happens. The talks will span decades and also span language paradigms, from WebAssembly to APL, from JavaScript to Kotlin, C++ to Lisp. You'll hear from designers, implementers, formalists, and the people building the tooling that makes all of that possible. In order to maintain a focus on cross-cutting concerns, that's what we want to achieve with today's workshop. We have split the day into 3 blocks, mixing different paradigms of programming languages and also different technologies and tools that are used for supporting standardization and language design. Just to give an example of how each block will be structured. So this morning, we will have a mature language and its approach to feature design. So it will be APL, and the design problem will be converging multiple implementations of a feature. Well, in that case, it will be JSON representation into a single language-wide notation. We then follow with a discussion of tooling for supporting the correctness and performance of the ECMAScript JavaScript specification. And then we will end the morning session with Hilo, which is a much newer language in early development. The afternoon and evening sessions will focus on current practices around standardization, ranging from Kotlin to P4. Whichever session you attend, you will have a mix of both languages and techniques to consider.
In addition to the broader program and the way that it's been structured, we also have 2 talks which will be bookmarking the workshop as a whole. The first is, of course, the opening keynote from Andreas Rossberg, and it starts us off discussing the state of the art in terms of the intersection between language design and specification. Our closing talk from Michael Sperber asks a very different question, and it's one that is existential, which is, for anyone who's working within the industry space, what role should requirements actually play on language design? Which should be quite interesting from an essential point of view. At this point, I would be very happy to introduce our keynote speaker, Andreas Rossberg. Andreas is one of the original and current designers of WebAssembly and the author of its formal specification. If you've worked with it, you've seen his fingerprints everywhere. Today, he'll kick us off and look at SpecTec, a new toolchain that rethinks how we write and maintain language specifications like WebAssembly. Please join me in welcoming Andreas Rossberg.
Okay, yeah, thank you very much for the invitation and the nice introduction. So obviously, I'm going to talk about WebAssembly and what we do with respect to standardization and formal specification. But first, like in a context where we talk about standards and formal language standards, there's one book you really have to mention, and that is this book. I don't know how many of you have seen that book before. It's the definition of standard ML. And ML, if you don't know, it's kind of like the parent of languages like OCaml today, maybe the uncle of Haskell or something. It was originally invented in the 70s. And you might not believe it, but it's one of the most influential languages out there. So it's single-handedly invented in the 70s parametric polymorphism, so people call generics in other communities, type inference, but really complete type inference, including inferring generic definitions. It invented, not quite invented, but adopted and made popular things like algebraic data types and pattern matching. It also was the first to have a really powerful and still unparalleled module system with higher order modules, so expressive power on the level of modules that is unparalleled. And most relevant for the topic today, it was the first language that had a complete formal specification. And that is this book. This book is the definition of Standard ML 1990. So this is a book from 35 years ago. This is what it looks inside, defining the entire language in terms of inference rules. And when I first encountered this as an undergrad, I think, in the 90s, in the mid-90s, I was really blown away because it was like so elegant, so concise, so precise, and so much better than anything I've seen before. So as a student, I've already grappled with like, okay, why do we have, I mean, we accept grammars, BNF grammars to describe syntax, but we have nothing analogous for semantics, right? Well, you would think semantics is way more important, but people are just using, you know, a combination of prose, hand waving, and wishful thinking, essentially, to describe languages. So this was, in my mind, so much better, leagues ahead of everything else. So in my naivety at the time, I was thinking, why is not everybody doing it that way? That's so obviously better. So it became kind of my vision to, you know, we should be doing it this way. But the authors actually of Standard ML, they didn't even stop there. They also went on as a research project, and that succeeded ultimately, like maybe 10 years later, to mechanize this definition. And mechanization means that you translate the whole thing into something that a proof assistant or a theorem prover can understand, and that you push all the proofs for especially soundness or type soundness for the type system through this theorem prover. And they succeeded with that, and that was the first proof of a full-blown general purpose programming language that it's actually safe, and that its definition is correct and makes sense, and that there's no undefined behavior in it. So that was another kind of milestone they achieved. But I mean, maybe first of all, why do we even care about formal specification, right? I'm sure there are many people who think this is just like sort of an academic exercise, and we don't really care. Well, the first obvious one is precision, right? No matter how much care you take with a prose definition, it will never be as precise as something you have to formulate in math, usually. So there's much less wiggle room for hand waving there if you have to express it in formulas. And the obvious one, I kind of already alluded to that, is correctness, right? If you do that right, the formalization, and push through it's called the meta theory, so proving things about the language and its definition, certain properties like type soundness, then you have a completely different level of assurance in the language definition and its semantics. So you can actually prove that certain things are correct and not just believe it or hope for it. And honestly, any language that claims to deliver certain properties, especially safety properties, especially through a complex type system, without actually formalizing it and proving it, you probably get it wrong, right? So I'm looking at you, Rust. And there are more reasons, though, and one is conciseness. So while this notation you just saw there might look very alien to you if you're not familiar with, I don't know, PL papers, right? So this is like routinely used and has been for 30 years probably in papers on programming languages, academic papers, and also textbooks. But of course, in industry and the mainstream, it's not really widely known. But at least my experience as a student who had never seen anything like this before, it maybe took me a week or something to pick up this notation and then go with it and feel like it's way more efficient to communicate what's going on than deserts of prose, right? That are just usually mostly boilerplate. And then there's a fourth reason, which is often overlooked. I think Yulia already kind of alluded to that as well, and that is how it connects with actual language design. Because if you have to formalize stuff, it really forces you to stay honest, right? So if you design a feature, I mean, basically a formalization, if you want, is like a super highly abstract on-paper implementation of your language in declarative form somehow. And if you design a paper that really has trouble being formalized within some framework, then usually that means you have committed a design sin. So if it turns out to be very inelegant or complicated, then you might want to rethink it. So this kind of creates a feedback loop in a similar way that doing prototype implementations on compilers or engines creates a feedback loop with the design process. So if you do it from the get-go, design with formalization in mind, then you get a cleaner language, I would claim. And I think with WebAssembly, WebAssembly is a case for that. Okay, so with that, I'm happy to say that with WebAssembly, we have achieved exactly this. It took only like 35 years to adopt it in the mainstream. And WebAssembly is fully formalized, and it has been fully formalized from the get-go. And when I say fully formalized, I really mean end-to-end. So that means from the very first byte of your input, like the binary format or the source text, to the last bit of what happens at runtime in computations. And what we use here is really just a textbook formalism. So things like you should be familiar with from papers if you're in that community. So anybody who has studied this kind of thing or read a few papers and understood them should immediately be able to pick up the meaning of the WebAssembly spec or the formalism in it. And also, maybe even more importantly, unlike other formalizations of mainstream languages, this is not just something on the side or that was done later or as a supplement. It's a normative part of the official standard. The whole standard is actually centered around the formal semantics. So we thought that is very important. So here is an excerpt from the WASM 2.0 spec. And there are two things you can see here. So one is these are the formal rules I mentioned, right? So this is like an excerpt that shows the execution of some branch instructions. But of course, we still have to assume that there is plenty of people in the audience who won't be able to read that stuff, right? So they expect some prose in the more traditional form. So we also have the equivalent prose explanation of what's going on. So the formalism is a kind of like declarative specification, and the prose is a more like algorithmic form. And ideally, they're supposed to be equivalent in some loose way, right? I mean, and if they are not, then that's a bug in the spec, essentially. Here is the similar thing for validation, so type checking of WebAssembly. And if you know PL stuff, then you also would immediately find these inference rules to describe typing familiar. But again, we have these prose statements as an equivalent. Okay, well, we did not stop there. We also mechanized WebAssembly. So this was, so currently up to WASM 2.0. WASM 3.0 is coming really soon now. So that was the WASM CERT project run by Philippa Gardner and Conrad Watt in London and Cambridge. And they put that in actually two theorem provers. So they worked on two mechanizations, one in Cork and one in Isabelle, and proved soundness. They also built an interpreter, a verified interpreter in Isabelle. So at this point, we have a machine verified soundness proof for actually the complete language. And I should stress that, right? It's not just some idealized subset, it's the complete language as specified. And that means we have real proof that WebAssembly not just believes or claims that it's well formed and everything, we have absolute proof that there is no undefined behavior whatsoever in this language. There's no unsafety. There isn't even any kind of underspecification, because pushing through the soundness proof means that you have to make sure that all the cases are covered, right? If you forget something, then the proof will fail. So there's no undefined behavior. You have some form of underspecification if you want, but not in the form of like saying, oh, this is just implementation defined and throw up our hands. Even in the places where we underspecify, we do it as a form of non-determinism. So we exactly specify the set of allowed behaviors that an implementation can pick from. So that enables us to actually state these soundness theorems in the spec itself. So this is from the appendix of WebAssembly, where we have, yes, this is the main theorem you really want in the end. That's syntactic type soundness. There are a couple of other properties stated in the spec, but this is like the most important one. But of course, there is a problem there as well, right? So WASM is not exactly a simple language anymore. It maybe used to be with 1.0, but we are way past that. So WebAssembly is pretty large. At this point, we have over 500 instructions in it. More than half of it are SIMD vector instructions, unfortunately. They're very high cost. And we also got a fairly non-trivial type system at this point. So where you have structural types, you have subtyping, you have type recursion and things like that. So even the typing level is no longer all that trivial. And this is like a table of contents from the WASM 3 draft. So you can see it has grown to roughly 240 pages now, plus another 70 pages of appendix that, like among other things, states these soundness properties and does the whole formal setup to prove that. And again, it's not just that it's already large, it's also growing fast. So since 1.0, we have added over 20 extensions, I think, roughly. Some of them fairly small, but some of them really substantial. And it's still missing some important features, like essentially the ability to compile control abstractions is probably the biggest ones, and threads, which are still not in that standing, unfortunately. So situation is that we have this spec, which is nice, but it's a lot of work. So the prose is really what it really is a handcrafted translation that I did manually from the formal rules. It's a transliteration of the formal rules into prose. So you can imagine that's a very laborious and also very error-prone process, and there are lots of obviously lots of bugs, smaller in it. And then there are other things that make it annoying, like that we have to use markup, and which is really a bad idea for a document of that size to use anything like markup or markdown as your format. I would never recommend that. And that is not, again, not just work that is done at some point. With every proposal, you have to repeat this duplicate work. And as I mentioned, there are quite a few proposals. 15 are we count as actually completed and more than 20 still active. And these proposals, they extend or modify the spec. And the way we do that is that the sources for the spec, they are on GitHub, and we do code reviews, and the reviewer usually is the editor of the spec, which mostly means me. So that can also be pretty painful because it's like so tedious, and also the LaTeX in it that defines the formalism is really hard to read. Like LaTeX is a write-only language essentially, right? Especially because in this tool we are using here, you can't use any LaTeX macros whatsoever. You have no environments, no macros, so everything is like manual. And these diffs can be pretty large. So the proposal for vector types I mentioned added more than 20,000 lines of code to the specification source. And then there are the mechanizations again, which have yet to do more work and also translate all that into their like notation. And that's definitely difficult for them because that's like an external project, more an academic project with very limited resources. So they have difficulties to keep up with the pace. So we obviously have like a scaling problem here, right? So we have solved the problem more or less of like, okay, applying formalism to a language, a real world language, but we have turned it into an engineering. How do we keep this going? And we kind of course, we knew when we started with this that we would have this problem, but at the time, what was it, 17 or something, we neither really had the resources nor the technology, nor did we really know the requirements of what would be needed to solve this problem. But things have improved. So recently, like 2 years ago, I think, we had a WebAssembly meeting in Dagstuhl, and there several groups joined up and talked. So one, that had done work in this space, and one was, of course, me and the other folks involved in the WASM spec. Then there was the WASM search team, so the ones that did the mechanizations. So they had a lot of experience with that side of the requirements, for example. And then there was Sukyung's group, Sukyung is here, who had previously worked in the JavaScript context on this toolchain called ES-Meta, which is extracting, if you want, the semantics from the natural language JavaScript specification. So they had a lot of experience with dealing with natural language in a language spec and connecting that up with semantics. So we got together in a room and realized, oh, you know, we might actually now have all the pieces we need to make something better here. So all the stars aligned at that point, and we were able to start this project that is now called SpecTec, and in essence is a DSL to describe the WebAssembly semantics. And this is the work of many people, various teams. I hope this list is complete because it's ever increasing. But yeah, many productive hours of work went into that. So, and what it does, it kind of turns the thing around, right? Instead of like worrying about the spec and then like writing it manually, we just generate it now from stuff that is written in SpecTec. Similarly, we can now generate parts of the mechanization, so at least all the definitions, and hopefully in the future also some of the more mechanical proofs. And we also turn around, invert what ES-Meta did, right? ES-Meta converted natural language into semantics, and we go the opposite way. We have a clearly defined semantics and we generate natural language from it, which arguably is the correct way around to do that. I think Sukyung would agree with that. So again, SpecTec is a DSL for defining the WASM semantics and authoring the spec. The definition then that we write in SpecTec is supposed to be the single source of truth for WebAssembly, for the meaning of WebAssembly, the definition of the language. And the toolchain around SpecTec can translate it into all the artifacts I mentioned. So that includes the math rendering, natural language, and COC definitions. And the natural language part, of course, is the particularly challenging one here. And the design goals were, of course, that it's not just easy to write and read, but also that it's easy to, that diffs work properly on that, right? Because, for example, the markup we were using, that is like super white space sensitive, and that is horrible for diffs, which makes it horrible for code reviews. So we very much avoided something like that. And then you have lots of goodies like meta-level error checking in the definitions, right? So when you forget something, you usually get an error from the toolchain. But I should also stress here, it's not in itself, although you describe a formal semantics, and it's not in itself like a proof system or a theorem prover. It's really just a preprocessor. So all the actual meta theory, if you want to do that, you would still be doing something like COC after it has been translated to something COC understands. So this is a new part now. WASM is not just formalized and mechanized, it's also generated from this formal semantics. And that covers all the 3 artifacts I mentioned. So the math, the prose, and still somewhat work in progress, the mechanizations. So currently, I think we have covered 1.0, but we're working on extending it to more things. And more importantly, this is not just something we did out of fun. A couple of months ago, the working group, the WASM working group, actually voted for adopting this as the official authoring tool now for the spec. So here's the page again I already showed earlier of the WASM 2 spec, and here's the sort of equivalent page of the WASM 3 spec. And there are some differences here which have to do with some refactorings we had we did for some of the rules, like the branch rule. So that looks slightly different, even the formalism. But in other cases, like the BRIF, that looks almost exactly the same. And noting that all this prose you see here is completely auto-generated essentially from this, right? Whereas before it was manually. Okay, so there are various advantages, obviously, of doing it here. So I want to summarize. The one is, of course, the hope that this decreases the turnaround time for designing and speccing new features, right? So you have more help and more error checking. You don't have to write the prose tediously. Just to give you an idea, when I first did the formalization of WebAssembly, it maybe took me like less than a week to write out the formal rules. And then it took me 2 months to translate that into English, right? That was just super tedious work. So we're hopefully saving most of that. And then there's the other advantage that there's much less room for human error now in translating all these things. And we have found plenty of smaller bugs in the spec while working on this. And everybody should benefit from that. And then there's the third thing, which has only developed more lately, is that, well, actually, there might be other uses of this machine-readable definition of the language. You could use it to generate other parts of tools. So, for example, ASTs for WebAssembly or other things. I'm going to get back to that if I have time in the end. So overall, the picture I always show is this. It's essentially kind of like a compiler pipeline, if you want. The input is your spec, your specification in SpecTec, and you have various internal representations, and then you have all these different backends that can spit out all the different things. And some of them are already done, some are work in progress, and some are kind of like anticipated in the future. And another thing we can do, we have this internal representation called the algorithmic language, which essentially is the AST for the English, right? But it's really just an AST for some form of language, so we can execute it. We can interpret that. So we also have this meta interpreter. And we can feed it the definition, and we can feed it some actual WebAssembly module, or many, actually the entire test suite, the official test suite, and it succeeds on the entire WebAssembly test suite. And the upshot of that is that we now have some assurance that the text you actually see in the spec is correct, because it's the same thing we were running, right? And in a similar fashion, once we have ported all the WASM cert proofs to the new backend, which is still, as I said, work in progress. So we have covered 1.0 right now. But once we're done with that, we have a similar kind of an assurance for the formalism in the spec, that is actually showing what you think it's showing, and that what we proved here, mechanized here, is the same thing more or less, because all of this is like auto-generated, right? There might still be bugs in there, but usually when you have bugs in that process, they show up more systematically. So all these little errors you have, they should be eliminated by that. So that is a level of assurance in the language specification, which I think has not been achieved before. Okay, so at this point, I thought I do something different this time and want to show you a little bit of SpecTec in interactively. So we're going to develop a little bit of SpecTec together. In form of the demo. Okay, now the screen rest has changed, so I want to adjust to that a little bit. Let me see. So obviously we don't have time here to do something super advanced, but let's define, that's maybe a bit too large, a tiny fragment of WebAssembly and call it nano-WASM. So when you specify a language formally, there are 4 things you have to do. The first is, the centerpiece is defining your abstract syntax. Then you also have to define the concrete syntax, and what you should do, and what most people are not doing, is specify how that actually translates into the abstract syntax. So concrete syntax in the case of WebAssembly means 2 things, the text format and the binary format. Then you have the static semantics, which is the type system, so validation. And then you have the dynamic semantics, which is the execution rules. And in the case of WebAssembly, that's like a small step reduction semantics. So let's do it like that. Let's start with syntax, abstract syntax more concretely. So these are just comments. So the way you do that in SpecTec is there is a way to declare abstract syntax, and the declaration is called syntax. So let's say for this fragment of the language, we just have two things. We have instructions and we have a subset of the official value types. So these are called val type in the WASM spec. And here we say we just have I32 and I64 as our value types. And you can read that either as a grammar sort of BNF if you want, or as a data type definition or an inductive type in a theorem prover. Both these interpretations would be okay. So that is an easy one. The more interesting one would be instructions. So let's say we have a drop instruction. So in I'm writing this all cap because that is part of the SpecTec syntax. That means it's sort of like a keyword or a constructor, and it will be typeset in a different way. We have, let's take the select instruction, and then we need, like the most basic thing is the const instruction. So the const instruction WebAssembly is a numeric constant, and it consists of a type for that constant and the actual constant. So this syntax is what we have to use in SpecTec, like you see in other languages, but this is not how the instruction syntax of WASM actually looks, right? But you can instruct the toolchain to pretty print it like that by adding a show hint here. So I could say something like, okay, whenever you encounter this thing, you should print it as if I had written this. So the const instruction is like type.const, and then the actual value is the immediate. So we have defined what val type is, but we have not defined what constant is. So that also needs syntax. And in reality, that would be like a bounded integer, a bounded natural number, but let's just keep it simple here. So just say it's an arbitrary natural number. So net is a built-in type in SpecTec. It's not that hard to make it bounded, but I don't have too much time to waste. So, and then let's say we also have locals. So locals, the local get and the local set instruction. And so they both take a local index as an immediate, and that's again a piece of thing we have to define. And again, that's actually a U32, but let's just stick with nat here for simplicity. So that would already be the abstract syntax of our language. And now let me check if I did everything all right. Okay, no complaints from SpecTec, so we're good so far. Let's go to validation then. So the type system. Typing rules are a relation between, in our case, sequences of instructions and types, instruction types. So SpecTec has a way to define relations. You have to give them a name. So let's say instr or k, and then you have to give it notation which defines the shape of the judgment for this relation. So it's something like instruction sequence. So we can use things like star and plus in the form of regular expressions. And that we are assigning something that is an instruction type. So what's an instruction type? Well, that defines or specifies what an instruction does to the stack intuitively, right? So there is a list of values it's going to pop from the stack, and a list of values it's going to push to the stack. And the arrow here is really just punctuation notation. So there's a bunch of symbols that SpecTec has built in that you can use to write out these kind of notations. It's not quite as advanced as something like Coq would give you, but sufficient for our purpose. So there's the naive typing relation, of course, this is not quite enough because some of our instructions like locals, they use something like the local index, and the typing depends on knowing what the local is, right? So what type the local has. So what you usually have is you have a typing context as well, and then people write it with this turnstile. So this holds under this context. And the context itself, we also have to define. And here, SpecTec offers some kind of record syntax. So because the context can have various parts to it. In our case, they're just locals, but in the real language, there are other kinds of definitions, of course, like functions and stuff. So here it's just a singleton record. And since locals and WASM are just indexed by natural numbers, we can just really list all the types of the locals as a sequence of their types, and then we can just index into this list essentially, or array if you want. So this is enough as an environment to record all the locals. Okay. Right, so this defines the shape, and now we have to give rules for that. And typically what you have is like one typing rule for every instruction. So a rule, you also have to say what relation it is a rule for, and then you have to give it a more specific name. So let's say we're defining the rule for drop. So you have a drop instruction, and what do we type it with? Well, the drop instruction takes some value from the stack, so some type T, and it doesn't push anything. So the return is the empty list, which you write as epsilon. And the T here, so SpecTec, should scroll up maybe a little bit. The T here, SpecTec will of course be able to infer that since this is an instruction type, and instruction type is defined like this, that this T is a meta variable for some value type. So that is an easy one. Let's look at select. So that starts out similarly. But select, if you don't know, is sort of like an eager if, right? So it has three operands, two being the two values that you want to pick from, and the third being a conditional like Boolean, which is encoded as an in, which tells you which one to pick. So you have two values, and the third value that is an I32, and you get back one of the two values. I'm using the same T here, which means, okay, this really has to be instantiated with the same type. So that's all there is to that. Then instruction, okay, const. That one is fairly easy too, because the const instruction actually has a type as part of its syntax itself, right? So it does not use anything from the stack. So now we have an apps on the left, but it returns a T, which is the same T that we declared. Okay, and now the other two, they actually use the context now. So for local get X, that doesn't need anything on the stack again, but it pushes some T. What is T? Well, that's the type of the local X, right? So where do we get that from? We look that up in the context C. So for that, you can write like premise, a site condition that uses some of the SpecTec meta syntax, like record selection. So we can project the locals out of the context, and we can index into the list that carries with X, and that gives us our T. And set is it's almost the same, except that the sites are switched around here. So that's that. And then we need one more rule, because these are just rules for individual instructions, right? So, but we're dealing with instruction sequences, so we need a rule that tells us how to type an instruction sequence. And essentially what we're doing is, well, there are very different ways to formulate it, but let's pick a symmetric one. So you have two instruction sequences. instr1 star and instr2 star. And here I really want them to be different in general, so I have to name them differently. So that altogether has some type. The sequence pops some T1s from the stack and pushes back some T2s. But what are these? And here again, we have to now inductively look at the individual instructions. So that is like an inductive premise. So we have to say what relation we're using for that premise. And here we are saying that the first instruction sequence has the type T1 star to some T star. And the other has matching type C instruction 2 star that goes from T star to T2 star. And that means that we can just plug them together, right? Because they're using the same T. And there's one final rule. We also need like the degenerate case of the empty instruction sequence, which is kind of trivial. So if you have no instructions whatsoever, then also nothing happens to your stack. Okay, so these are the typing rules for the entire thing. And if you know how type systems work, nothing of that should be surprising. It should actually be completely boring. Okay, and I actually did not screw up. So the other interesting bit is execution. What is execution? So we're using a small step reduction relation for various reasons. One being that we need to be able to model states as threads and interleaving. So a small step reduction is you define a relation from program configurations to program configurations, which models like one step of computation. So you again have a relation, let's call it step, and it maps a configuration to a new configuration. So what's a configuration? Well, part of it is the sequence of instructions that we want to execute, evaluate. And we want to reduce that successively to a simpler instruction sequence. But there's more, since we also have state. In this language or fragment, the state is relatively simple. We only have locals. Locals are stored in the frame of the current function. So we're going to have something here in the configuration, which is the current frame. And the current frame is, again, simple here, just contains the locals, so we can do the analog thing like we did with context and just have a list of them here. But this time they are not types, they are actual values in there. And what's a value? So in a reduction semantics, the way it works is you have some broader syntax of expressions or instructions, and you reduce that until you have reached something that's of value form. And that means that you have to identify a subset of your syntax that are the values. In our language, we can use the const instruction as that subset. So I can just redefine that here, and SpecTec will realize that this is a syntax subset or a subtype of the broader language. And then the idea is we keep stepping until this instruction sequence has been reduced to a sequence of just values. And you can view that as the resulting stack, right? So the stack of values we end up with. And yeah, WebAssembly has multiple return values, so there can be many of that. So that's kind of the setup. And then again, we have to do the rules. So the first one is for drop. So we have some frame and a drop instruction. And what do we reduce that to? Well, we can't actually reduce drop alone. Drop takes something from the stack. So we said we model the stack by essentially a sequence of values. So we have a value instruction before the drop. And when we have this paired up, then they can react and be reduced to the empty instruction sequence. Basically, they cancel each other out. And I also have to put the new f frame here, which has not changed. Okay. Select. Oops. Select now takes 3 values from the stack. So a val1, a val2, and the third one, which we know from validation has to be a constant, an I32 constant. So we can pattern match that more directly. And if that is followed by select, well, there are 2 cases actually. One is that the n is 0, and the other is that it's non-zero. So we actually need 2 rules here. One for the true case, in which case it would go to val1. So we throw everything away except the value we want to keep. So we need a side condition here, like before, which is if n is not 0. Okay. And then there is the symmetric one for false, which just differs by returning val2. And that is really all you want to know about what an if does, essentially, right? Like, you don't want to read a page of text to understand what an if does. This is the essence of it. There is no rule for const itself because we said it's actually already a value, so there's nothing to do in terms of a reduction relation. But we still have the locals. There, local get. So local get does not use any operands. It does not, but it returns some value. And where does it take it from? Well, again, we, like in the static semantics, we can look it up from the context. This time the frame, actually. So we can look at the locals in there, and that gives us our value. Okay. And then lastly, local set is the one that actually modifies the state. So something slightly more interesting is going to happen here. So first of all, it expects a value on the stack. And then it reduces to something. Well, it reduces to the empty sequence because we're done after that. It's only executed for the side effect. Oops, I made a typo here. But it reduces to a different f. So we have now want to change f. Scroll up a little bit because you might not be able to see it at the bottom. And there's again more notation that SpecTec has for modifying something like this. So the notation we use is something like this. You can say this is the same as f, but with the component local x replaced by val, regardless of what it was before. Okay. And that is our execution semantics. And let's see if we got it right. No, we did not. 65. All right, yeah. So this is telling me, oh, this is a value, but I actually expect a configuration here. So I have to put the F here. I forgot to put the F, and I also put it here. And this should be locals. So this is exactly the kind of typos that we have plenty of in the spec that we now no longer have. And now we are through with that. So that is our specification for NanoWasm. I did not show you the binary format. That's another thing you can do now. But instead, I want to show you something else, which is I prepared this little document skeleton. So in Sphinx, this markup format we're using. So that is just written text here, like you would write a Sphinx document with markup for, I don't know, headers and italics and stuff. But in it, you see these, what we call splices. So these are things that SpecTec can now look for and replace with whatever you said it should replace it with. So this would replace this splice with the syntax definition for val type and instruction type. You can also have inline ones, which are just expressions it would typeset nicely. Like a math thing, but knowing all the hyperlinking and stuff that the spec has to do. And then you have ones where you can insert rules. And there are two versions of that. The plain rule is inserting the rule for the formal rule for it. And then you have rule prose, which generates the whole prose for that. So so I have a make file now because I prepared that because it's a bit tedious to invoke it that way. So that ran successfully, and what it spit out is this. So it's the same skeleton, but now with all the stuff inserted, including maybe down here you see some of it. This is some of the prose it inserted. So which already looks kind of ugly with all the math markup. So you can imagine how tedious that is to write manually, right? And you see here, for example, is select. There's a bit more text here generated. So we can also actually look at the PDF. Right. And this is our PDF that it generated nicely with table of contents. So that was done by Sphinx, but then here are our splice definitions. So this text I wrote manually in the skeleton is kind of editorial text, but then there's other text like here in the rules, or more interestingly, the rule for select that is all generated. Just the specification you saw before. Okay, how am I on time? I think I should wrap up, right? Oh, really? Okay. Oh, that's good. So actually, I can show you the one thing I skipped in because I also prepared that. So this is how we define the binary, the concrete syntax, the binary format. So we have something like attribute grammars essentially. So they read like grammars, but they also have a right-hand side that tells what they produce, right? So for example, if you have to parse or decode a val type, there are two cases. They're just single bytes. So these are essentially our terminal tokens are just bytes in this case. And this is the abstract syntax you get out. Or maybe more interestingly here. So these are some of the instructions, and I might have gotten the opcodes wrong, actually. I'm not sure I can always remember them correctly. And some of them, like const, that is not just a byte, but it also has something after it, an immediate. So that is syntax I defined for natural numbers, and I can match on the AST created by that, the attribute synthesized by this production, and use it here to synthesize the larger one. And for example, where this is a bit more interesting is for natural numbers, WebAssembly uses the LEB format, which is like a variable length format to encode integers or natural numbers in this case, which uses the most significant bit of every byte to say whether there are more coming for that integer. So you have two cases. One is there's only a byte, and that byte has not, the most significant bit is not set, then the value of our number is just that byte. If you have a byte where that is set, then you expect like iteratively more to come, another natural number if you want, and then you can compute the actual value by, erasing that bit and then do the usual like multiplication, right? So this is a grammar for LEBs. In the actual WebAssembly specification, it's a bit more complicated because we have some restrictions saying that it cannot be overlong. So if you're encoding a U32, it must at most be 5 bytes or something like that. And you can encode all that, but it gets a bit more complicated. And yeah, and this is what the spec for that would be. So really just the ASCII art of the same thing, right? And that's the point. It's supposed to be sort of like WYSIWYG if you want. It's just ASCII of the formalism you get. Okay. So I mentioned that there might be other use cases. So recently we had another meeting where we discussed like possibilities of things that could be done. So I already mentioned this meta interpreter that we have. That is not technically not something that's actually generated because it's a handwritten interpreter that runs on the AL, that executes the AL, which is a fixed language. So it's on the meta level. But we could generate an actual WebAssembly interpreter, for example. So part of the WebAssembly standard is that we have this reference interpreter, which I'm also maintaining, which is written in OCaml. And that is a kind of like another manual transliteration of the formal rules into something like OCaml. And you could imagine that you could generate at least parts of that. But there are other things people were interested in, like maybe executing the reduction semantics more directly, right, without going to the algorithmic formulation. So you also want to use the rewrite semantics to really execute the reduction semantics verbatim. There are folks who are interested in doing symbolic interpretation for WebAssembly for certain proofs and stuff, or reasoning about programs. So that kind of thing could be generated. There's somebody who's working on having a different representation of the WebAssembly execution semantics in CPS form, which is more compositional. It's kind of like a big step semantics. So all these things. You could generate parsers from the grammar specification, or decoders, which we usually call the parser for the binary format. You could generate AST definitions and various operations on these AST. For example, Thomas Lively, who's the main maintainer of Binarian, this code manipulation and optimization tool for WASM, he's looking into that and might want to use it to generate his AST definition for C++, right? Because it's a huge set of class definitions and would be more convenient if you could automate that. And I mean, more ambitiously, why just stop at interpreters? You could generate a compiler if you wanted to, right? Maybe not the most efficient one, but just the idea that you could just do that from the machine-readable specification is already interesting. And there are actually quite a few consumers of WebAssembly who don't really care about performance. They use WebAssembly primarily as a secure sandbox, in particular on embedded devices and things also you usually don't care about hyper-optimizing it. And in their case, this might well be enough, right? If you have a tool that could do that, why not? And if you're into program verification, then you could generate program logics for WebAssembly from its semantics. And finally, maybe the most immediately applicable thing that Dongjun, one of Sukyung's students, is already working on is generating tests, right? So WebAssembly has a pretty extensive test suite, but its quality varies quite a bit. So there are features that are covered well, there are features that are not covered so well because it all is handwritten, right? And you have to handwrite WebAssembly, which is like, not so much fun. But we can now write a fuzzer tool that not just understands the syntax of WebAssembly, it understands the semantics of WebAssembly, right? So for one, it can predict what the supposed outcome is of any code it generates. So it can auto-generate all the assertions, but it can also look at some of the rules. So for example, say we have the memory fill instruction, which is a thing that fills a range in memory with some byte value. Yeah, so slight generalization of zeroing out memory. And the reduction rule for that looks like this, or maybe in typeset form, it's a bit more readable. And you can just look at this rule as an example and figure out, well, these are the meta variables I can instantiate. What are the possible instantiations? And then you could do some like quick check kind of thing, instantiating with all the interesting values and generating the test matrix from that, right? Instead of having that to do that by hand. For some things that's easy, for some things it's not so easy, but the general idea definitely is appealing. And not just that, you can also use that to mutate it to generate negative tests, which is also very important, right? So you can exactly figure out, okay, how do I have to vary this so that it would not be valid? And you want to cover that as well. And there are a number of negative tests in the WebAssembly test suite, but not so many because people are usually not very excited with writing that, or that's not what they need to test their system usually. And I think, Jaeyun, you will talk about that in the context of P4 SpecTec a little bit? Okay. Right. So yeah, the idea is, sorry, I skipped over part of the animation, that from the definitions, you can infer the domain of all these variables, right? And then generate like skeletons like this. There are a few more things I could say here. One is that the question we usually get from people who have also worked in this area of like having tools for formalization is, okay, why did you invent your own thing? There are tools out there. One famous one, established one was Art Lam, that was done like in Cambridge some 10, 20 years ago, which tried to solve a similar problem. You could like really write out rules and semantics and could generate LaTeX for you and other things. The problem is that this tool was way more general and tried to solve a much more general problem. And that made it very hard to adapt to a concrete use case and do exactly what we need here. Whereas by developing our own thing, we can just shamelessly specialize it to our problem and cut so many corners wherever we need to or want to, right? And we are in full control of the tool. So we can build in all the meta notation that's used in the specification. So you saw like this record notation I used and indexing and stuff. That's just built into SpecTec. It's not part of WebAssembly, it's part of the meta language to describe WebAssembly, right? So SpecTec is really, the feature set it has is exactly the meta language we need for the spec. It does not have anything WebAssembly specific itself in it at all. So you could in principle use it for something completely different, but you might need a different set of meta level features as well for that. Right? So one thing it does not have, for example, that I usually tell people when they come up with a question like, oh, can I use it for this? Yeah, for example, you don't have binders, right? There are two main things you don't have support for directly. One is binders, one is, at least for now, evaluation contexts. If you know programming language semantics, these are very convenient things to have. Binders, okay, maybe that's just, you can still roll your own, and that's actually what you do elsewhere as well. Evaluation contexts kind of sad that you can't use them, but one thing they would complicate is some of the backends, like how would you translate that to something like Coq? So we haven't really solved that problem yet. So the other thing that's important here is that, yeah, I said we can cut corners. That means that various backends can make varying assumptions that are specific to the domain they're operating in. So if you remember this pipeline I showed you, there are all the different backends. And some of them make like almost zero assumptions, like the LaTeX renderer, that's pretty straightforward. That just translates it, and you can write any relation you want, and it will just typeset it. But of course, if you want to generate prose, let alone an interpreter, then you have to make certain assumptions about how to interpret these relations as execution rules and things like that. What are these configurations? And so that is hard-coded in these backends. So all the edges make different sets of assumptions. But yeah, specializing it drastically simplifies the problem overall. And we control the implementation, so we can just tweak it whenever we need to. So that means that we don't have dependencies like we would have when we use an external tool. Remember, this is an industrial standard, right? So we have to be able to maintain this for at least 20 years. So depending on some academic project with an unclear future would be highly risky. But of course, we trade that for a bus factor. So the tool we build ourselves is also not trivial. And there are only very few people who really understand it and can maintain it. So that certainly is sort of a not really solved problem either. And I openly admit that. We have some ideas, and there's funding, a lot of funding and grant proposals and stuff, but we don't really yet have a long-term story of like, maybe there should be some foundation or whatever that finances that stuff, but that doesn't exist yet. And there are various limitations. So the user experience, I mean, you saw one of the error messages, it was not particularly pretty. But you got an error message that's also not necessarily a given. It might also just crash on you with an exception. And And of course, the prose that could be endlessly tweaked, right? There are cases where it does not produce something as nice as you would write by hand, and that's open-ended. I mentioned that it doesn't have evaluation context, so we really would like to have them. Right now, we can mostly avoid them by just having manual context rules, like the one I showed for execution. Oh, did I actually? Maybe I've missed that. But one proposal we are working on is stack switching, what it's called, and essentially it's adding delimited continuations to WebAssembly as a way to compile control abstractions. And if you want to model the execution of that, you really want evaluation context because it gets very clumsy otherwise. I think this is mostly repeating things I already said. One thing I should also mention about the meta interpreter, that is really only doing the execution semantics. It does not meta interpret the typing rules, for example. And that is a non-trivial problem because we have a non-trivial type system with subtyping and transitivity rules. So deriving an algorithm from that is not exactly trivial. In an ideal future, we will eventually cover all that. Also, the other two things it doesn't do is the decoding right now. That's the thing we can hopefully address. And some of the numeric stuff, it also doesn't implement itself. And all these other things are just currently imported from the reference interpreter. So all that is in OCaml, so we can just grab that. But yeah, in an ideal future, we want to reduce that set of external dependencies or executing. Yeah. Oh. Where's my summary slide? I lost my summary slide. Okay, well, I think I can wrap up anyway. So as you saw, like, we really, like the WebAssembly group as a whole, takes quite a bit of pride in having made that leap to having a formal language specification. Because as I usually put it, like, before that, we have basically been stuck in the 60s, right? The state of the art of industrial language specification has not really changed since the 60s. I think the last language that made a big leap there was Algol 68, but that was sort of like an evolutionary dead end, in a way, unfortunately. And since then, it's all like, okay, we have grammars, but everything else is just prose. So we really wanted to take this to a new level. And we kind of pushed it a few decades ahead, but in an ideal future, I would like to push it further ahead. So we have this whole proposal process for WebAssembly where as a champion for a new feature, you have to deliver all these things. You have to deliver SpecTec, spec text, you have to deliver the formalization. That's your responsibility, or you have to find somebody who can do that. What we don't require yet is the mechanization, because that technology isn't quite there yet, and that would be quite a burden on people, like, because you really still need experts for that kind of thing. But maybe in another 20 years, we can reach a state where that is also a natural part of the process. So you not just have to come up with the formal semantics, you actually have to mechanize it. Hopefully with tools that are more mature and advanced and automated. Yeah, and I think I'll leave it at that. Thank you very much.
We start about the lecture by talking about that WebAssembly is fully specified, like end to end, like we have mechanized proofs available, and that the challenge was mostly like for the maintainers to sync all those different artifacts that we have.
Yeah, to maintain the thing, right? Like, and
okay, and the solution there is like a DSL, like SpecTec, for example, that you adopted, for example, like to synthesize the different.
Yeah.
So my question there is like, what of those principles like that you highlighted in the beginning about WebAssembly do apply to SpecTec itself? So for example, is SpecTec like specified, or for example,
that's an excellent question. So that's also one of the, I think I had that on the limitation slide. Maybe I didn't. So some of the things we want to do is develop an actual meta theory for SpecTec. I mean, I said it's a preprocessor, right? So it's some of it, especially like the external language that kind of tries to understand math notation. That's a bit hacky, and it's translated, elaborated in some internal language, and that actually has a relatively clean semantics that we could specify. And I actually at some point started doing that in SpecTec. But one of the grant proposals that we have, that Sam Lindley and Philippa Gardner have submitted just recently, is part of that is having a meta theory for SpecTec itself. But right now we don't have that yet because our primary goal was actually replacing the toolchain and then to alleviate that pain, and then we can see what the next priorities are from there. But we definitely want to do that as well.
Okay, I also have another question that you already touched on a bit, like in your shortcomings. So for example, you were talking about the bus factor and that like the user experience, for example, that people like issues that might arise. So my question is like, how many users are anticipated to use SpecTec, for example?
Well, that's a good question. So it's hard to predict. I don't think it will be many, right? So it will still be a specialist tool, definitely, right? Because how many people do we have that to put forth proposals? So it would be a 2-digit number at best, right? So that's also why I'm not too worried about it having some rough edges in terms of user experience, because at this point we don't care that much, and they can probably put up with that. It's still better than what they had before, hopefully. Of course, that story might differ if other people pick this up. And I mean, Jayun will talk about P4 SpecTec this afternoon. So that's applying the same ideas and part of the same code to P4, specifying that. So if that becomes more of a thing and successful and we have a broader user base, then of course the story might change. But right now we're not focusing on that because we don't want to be slowed down by having to worry about too many use cases.
So based on your demo, like you definitely saw that you're an expert user of
SpecTec.
You don't need kind of like, you have syntax highlighting, you don't need any kind of like additional IDE support. You can fix your bugs quickly, like in the specification. But since SpecTec like is an external DSL, for example, like you have all the issues that there is like no tooling support,
right?
Like there's no IDE plugins, there's like no mature tooling like that people can use. So that loops in a bit like to my first question, like that I had is so it would be great like if you can then also like synthesize part of like your SpecTec implementation or IDE plugins and so on, like from a like
but one problem at a time. And I mean, it's always the question of what do you compare it to? There was no such tool support before for any of the spec writing either, right? It was actually a much worse tool chain in many ways that broke all the time. And what broke were external dependencies, right? And then we always had to figure out, okay, why is it breaking now? I hadn't changed anything. All of a sudden it doesn't compile anymore. And then you have to go into the change history of BikeShed and figure out what crappy syntax they added that interferes with the LaTeX that's embedded in HTML in our case and just does random things. And so we're getting rid of some of that at least. And so, relative to that, we're good. But I agree. I mean, having an IDE would still be way better.
Okay, thank you.
Heartwarming talk, thank you. Can you use SpecTec to also state the properties you want? Milner, we get the well-typed programs do not go wrong. I stated at least I put it.
Right. That's also an excellent question. We have talked about exactly that a couple of weeks ago. And some of the people working on the mechanization backends, they would like to have that ability so that you can at least express the theorems and they get somehow translated as well. Right now you can't. But that would be awesome because, I mean, we have them in the spec, right? So if we could render that as well, that would be great, even just from that perspective. But of course, it's somewhat non-trivial because the way you actually formulate some of these properties depends a lot on the theorem prover you're using. So we have to find some form that is kind of like general enough so that they can all use it in some form. This is basically active research figuring out what that form could be. But yeah, we would love to have that.
I wanted to ask, how much are you inspired or at least aware of the tooling that the CPU people use to specify license space?
So yeah, I mean, we definitely looked at all the things like Sail and stuff, right? Not me personally. I'm not very familiar with that, but people like Konrad know that stuff a little bit, and he's from Cambridge, right? So yeah, so I think we looked more or less at all the marketplace to some extent, but some of the requirements are quite different as well. So I can't answer anything specifically about that, but yeah.
So I have a question. Maybe you could talk a little bit more about the animation step, how they get from the rules to the prose.
Yeah, the experts for that would be sitting there. So, right. So maybe I should explain. So in this picture, oh, there it was. So I showed you before that the LaTeX, the formalism is kind of declarative, and then the prose is algorithmic, right? And one of the problems here that you have to solve is getting from declarative to algorithmic. And in some of the formalization world that has something like that has been named animation, like you animate your reduction rule. And we have something similar as well. So I can't really speak for the inner workings of that. But basically, yeah, you interpret the reduction rules in certain ways. So you have to know what a reduction relation is. That's part of the hard-coded knowledge on that edge. And then you pattern match on the left-hand side, and you can turn that into a function essentially, right? Like on your input. And then the only thing you have to add really is how do you find the redex, so the next instruction to invoke. And I think what the animation currently does, it actually makes the stack primitive, more primitive, so it doesn't even have to search for the redex. I mean, for this language, actually, it's not that hard because it's like a relatively low-level, primitive, very sequential language, and all the reduction rules are relatively straightforward to read. But I could imagine that I mean, for some cases, it's actually not trivial, especially when you have more interesting things going on with the context in the store and the frames, and things like branches. But I could imagine that for more structured languages, that might be a harder problem. But yeah.
Any more questions?